Professor Alfred here from University of Michigan, who will talk today to us about sparse matrix approximations. As always, I would like to ask everyone to mute yourself out during the talk and then unmute as you want to ask questions. Al, the audience is yours.
Very good. Thank you very much, Wojtek. I'm, as I was saying before, really happy to be able to address you virtually on a topic which has been close to us for the past 10 or 15 years or so, in coming up with methods and theory for sparse approximation, in this case of matrices of a special type, covariance matrices and inverse covariance matrices. So I'm going to talk a little bit about the framework, sort of introduction of tensor value data and how this covariance approximation or inverse covariance approximation comes in the picture, and then talk about a couple of approximations that one is pretty old, some work that we did back in the 2012 area, and Kronecker approximation, and then sparse approximation of the inverse covariance that represents recent work. And then I'll be talking about a really cool application of all this. Let me first go into full screen mode here. So we have the full landscape. Right, well, I just told you about that. So the application is the NASA Solar Dynamics Observatory data, which I'll talk about in just a minute. If you're interested in a little more information, you can go to some of these papers that I've listed here on the Kronecker PCA that I'll be talking about, Kronecker product PCA, and then the so-called tensor graphical lasso and the Sylvester graphical lasso, or SIG lasso for short. Of course, I need to acknowledge all my current sponsors. So here's the application that motivates this high-dimensional sparse matrix approximation problem, predicting and identifying solar events. So what you probably know is that the sun is a very usually benign source of light, energy, and on the other hand, it occasionally has very, very severe, intense solar flare activity. And this solar flare activity can be so bad that it can cause havoc on Earth if the flare happens to fly off of the coronosphere in our direction. And we have about somewhere between 12 and 24 hours to before the ionic storm hits the Earth. And when it does, if it's strong enough, it can knock out lots of things. Back in the 1800s, it actually knocked out most of the telegraph system. Today, of course, lots more could be knocked out. GPS, our energy grid, just about every electronic communication medium we have would be severely affected, and has been. In Sweden, in fact, just a few years ago, there was a flare event that caused their airspace to be shut down for a period of time because of their lack of ability to communicate with incoming aircraft. So there's several types of flares. They come in flavors, intensity, labels. X for extreme, those are the dangerous ones, down to class B, which are, they're interesting phenomena, but they don't cause any measurable solar wind around the Earth. So the effort here is to build from a matrix of observations over time with various sensors, and there are several satellites that orbit around the sun and collect different types of information about electromagnetic fields and atmospheric activity on the sun. So you have this tremendously large data matrix. You have images that have thousands of pixels from different modalities evolving over time, and you want to use this somehow as a function of time to give that warning with maybe an hour to 24 hours prior notice, so that one can take precautions against these flares on Earth. So we can define this this data as a tensor valued, or what's called multi-way data cube, k-way, where k might be the modalities of this space dynamic observatory satellite plus time. And there are d total dimensions, which are the product of the dimensions in each of the tensor modes. mk is going to become an important quantity. It's the codimension relative to dimension k, that is the product of all the other dimensions, which can be quite large. So z is our data now, and we have to deal with some common traits if we want to build some sort of predictive mechanism. Those traits are that there's lots of diversity in the indices, types of indices, in the mode dimensions, and hopefully we can take advantage of some form of sparsity. Unfortunately, in the case of solar flare prediction, there is no sparsity. It's not as if we have a lot of pixels that have the same value, right? It's basically a turbulent natural phenomenon that's being measured in an image. But something else might have sparsity, and that something else is going to be covariance or inverse covariance, which I'll explain in a minute, why it's reasonable to assume that that might be sparse. And so we have this data cube that might be sparse. Maybe it's also low dimensional, a few degrees of freedom that we may be able to build an approximation to for the purposes of building a predictor, right? We know that prediction requires the some measure of dependency of the future on the present and the past, right? If you want to predict something, you need to have that measure of dependency in order to propagate forward your forecasts. And that dependency can be encapsulated through the covariance or inverse covariance. So the data cube is non-deterministic. So a first order approximation, which is the standard sort of tensor multi-way data analysis approach, isn't going to work in this case, because these are not images of faces of simple objects that you might be able to assume that you can estimate some sort of mean that's meaningful. And of course, as I just said, you need a second order information, the covariance of this data matrix, in order to perform any kind of forecasting, where that covariance might be conditioned on this data cube coming from the precursor video frames to a really strong flare versus another covariance that comes from a weak, a precursor of a weak flare, right? And then you can use discriminant analysis, hypothesis testing to test whether you're in a weak or a strong regime. And so the second order approximations that we're going to be talking about, the tensor approximations, are like the ones that are used in first order analysis. They are Kronecker products or Kronecker sums. And I'm now going to motivate why there's some hope in being able to apply a Kronecker type of representation to a covariance. So here on this slide, we have our time and space. I'm just looking at one modality here for the data cube. Width and height, of course, are then going to be concatenated into a single variable by, say, lexicographic indexing. So what you get is over 2 dimensions, d1 being time and this d2 being the product of width and height, number of pixels, a matrix X, which can be then vectorized, right? Stack all of the columns on top of each other. So each column is a spatial snapshot at a particular time of this solar activity. And so if you look at the covariance of this vectorized version of this data matrix, what you end up with is a highly patterned matrix in terms of the blocks that appear to characterize these correlations between 2 spatial snapshots. So between snapshot 1 and 2, you have this correlation matrix. And so this correlation matrix has a fixed dimension, right? It's a D2 by D2 matrix, number of pixels by number of pixels. And the simplest possible assumption that one might make is that all of these spatial correlations can be summarized as the same spatial correlation matrix or covariance matrix times a scalar quantity, which is the temporal correlation between time 1 and 2. So that leads to this Kronecker product representation. Very simple. It's saying that it's that this matrix, which has this patterning, is actually highly regular because in every spatial location you have the same covariance structure, the same, relative magnitudes of correlations. The only thing that captures the time variable is this scalar that changes from time lag to time lag. So that type of model is perhaps questioned as why would one ever want to use such a simple model? Well, I'm going to motivate this simple model, Kronecker product model, by a fairly general class of processes. That is, processes that obey a differential equation, a partial differential equation over time. So U here is the observation over continuous time and over continuous space, X, Y, and Z. Or actually, it's only the plane here, X and Y, with a partial relative to X and Y here. And that's and then there's some disturbance, W, some random disturbance. So this governs a lot of physical processes, right, that obey, in this case, a linear partial differential equation. And one can then express this in terms of differential operator equivalent using Kronecker products, operator products that in Euler discretized form, so you just do an Euler discretization over time and over space, convert this this differential equation into an equivalent equation which has this form of a Kronecker product, either on the vectorized version of U that goes over time and over all the spatial components, like in the example I showed above, or you can also represent that in terms of a rectangular matrix, time by space dimensions. And so this is a differential equation in difference form. Oops, sorry about that. And in finite difference form. And so you have this generative function where U is the observation. dt and dz are differential operators, so they're sparse, right? They're incremental operators operating over only neighborhoods of order 1 of any particular time pixel location. And W is this matrix of random disturbances. So using this property that of Kronecker products that I describe up here, and this representation that we just derived, if you make the assumption that W is a disturbance that is stochastic, it's maybe a Brownian motion or a white noise that has, of course, identity covariance with a factor sigma squared, then the inverse covariance of U is the Kronecker product of A Kronecker B, right? Where A and B are dz and dt, or dt and dz, because we're taking a covariance outer product, right? So that they become non-negative definite matrices. And so those are sparse because we know that these differential operators are incremental operators, so the matrices are very sparse. So the inverse covariance of any process that satisfies this type of differential equation is going to be sparse. That doesn't mean that the covariance is sparse, but the inverse covariance should be sparse if it satisfies such an equation. So, for example, there's one equation which is very much of interest to us because it's been proposed for modeling the magnetic fluctuation of the solar plasma on the surface, and that's the diffusive limit of the magnetic induction equation, which is of the form of a Laplacian operator. So the mixed derivative is equal to 0, right, in this Laplacian operator. And so then that, of course, is equivalent, this equation, this magnetic induction equation, which I'm going to be calling MIE, is going to be equivalent to this matrix in the discrete Euler finite difference domain, which drives this W disturbance that drives U indirectly through these sparse incremental operators. Right. So for this example, we have a discretized realization of this process U over a 2D space. Then its inverse covariance is sparse. And here's an illustration for an 8x8 image and 16 time points. So that's we've discretized space and time so that we get this matrix or a tensor, three-way tensor with space-time support 8, 8, 16. And so the inverse covariance is this highly structured pentadiagonal matrix, sparse, most elements are 0, with a well established structure that is inherited directly from the stencil that is associated with the Euler discretization of the MIE, the magnetic induction equation. Okay, so sparsity in the inverse covariance, even though the realizations may not be sparse at all, they're Gaussian, filtered Gaussian, filtered through these differential equations. And this just shows the various stencils for 8x8 frame for DZ, and then for the DZ transpose, which is what plays into the covariance, because that's what we've defined as B. DT transpose is A in A Kronecker B. All right, so here's just a realization. One can generate realizations easily using these Euler discretizations and the characterization of the inverse covariance. You simply use the Koleski, or sometimes called the Bartlett decomposition of the positive definite covariance, and then apply that to independent, identically distributed white noise over space and time. So a one-dimensional representation, you might ask, can we go further than that? Can we go to maybe a case where we want to model long-term dependency in these equations, where the time and length scales don't decay as they do in these in these differential equation models, stable differential equation models. And so Kronecker product, a sum of Kronecker products is another another approximation, but of course more general. And so one can define these just like a singular value decomposition of a function or a matrix. This is a different type of decomposition. It's a Kronecker product decomposition, which has constraints that the norms of A and B are equal to 1, and the sigma I is greater than 0, where R denotes the rank, and R is less than equal to D1 times D2. And so we consider this optimization in terms of an approximation now for a Kronecker product, where the approximation is over all matrices AI and BI of identical dimension. Over all of these, and this should actually be D1 by D1 and D2 by D2. That's incorrect. These are square matrices. That's a typo. So over all these matrices, these square matrices, we want to find a lambda hat of this type, this form, which minimizes this objective function, where we have a nuclear norm that incorporates sparsity on the sigma I spectrum, right? Or it incorporates our prior knowledge on what the rank should be. So there's a very simple solution to this optimization, and that was published about 7-8 years ago, which says that all you need to do is to note the fact, these are the Frobenius norms here, that the Frobenius norm is invariant to any kind of rearrangement of the elements of the matrices of which they are measuring. And so you can define then the rearrangement operator R and its inverse, which basically rearranges a square matrix which has dimension D1, D2 by D1, D2 into a rectangular matrix, which is constructed by taking each one of those pattern spatial covariance components and unwrapping those into a vector and then replicating those vectors over all the time points. So it's a rectangular D1 squared by D2 squared. And so now when you do that, this becomes a simple minimum eigen or singular value decomposition problem, where the penalty comes in through a shrinkage operator, the standard argument, and UI and VI are the singular vectors of the AI and BI respectively. So excuse me, they're the singular vectors of lambda, right? Not of AI and BI result from this optimization. So UI and VI are the singular vectors of lambda, which turn out to be identical to these square matrix AI and BI when you rearrange these singular vectors back into, right? These are singular vectors are D1 squared by D2 squared, D1 squared and D2 squared respectively. You rearrange those back into D1 by D1 and D2 by D2 matrices, and those are these Kronecker singular matrices or singular vectors, you might call them. Okay, so why does this make sense? Well, if you actually have a rank 1 covariance, like in the magnetic induction equation or any other differential equation of the type I just showed, then R is equal to 1. The Kronecker PCA spectrum, which is simply the plot of the sigma i's over I ordered, is 0, except for the most significant, that is the principal component, principal KPCA component, whereas the PCA spectrum is all splattered over the eigenspace. So this concentrates the eigen space into one dimension spanned by this Kronecker product, A1 Kronecker B1, where A1 and B1 are determined by the rearrangement squaring a rectangle, squaring a vector where the vectors are left and right singular vectors of the covariance. So principal component of KPCA fits 100% of the covariance, whereas principal component PCA fits only 2%. If you add noise, then KPCA drops in terms of fitting with a single component, because there's sampling variation in your covariance. So you only get 82% in the first component with some drop off in the higher order components, but principal PCA component still only fits a very small percentage, only 1%. These are for the sample covariance, right, which I define as the realizations from a random process, in this case a Gaussian random process, multivariate, with covariance equal to this rank 1 MIE. These are simulated from the MIE equation. And so you can see that this decomposition, rank 1 decomposition in KPCA, compares rather favorably with PCA. So Kronecker PCA, here's the true covariance for this MIE equation, 32 by 32 pixels, 12 samples over time, 1,000 statistical samples. The sample covariance is a bit noisy, and as we know in PCA, if you use a good size, right-sized subspace, you can reject the noise. Well, rank 1 size subspace of dimension 1 is not adequate for the PCA, but for Kronecker PCA, we can see indeed it does have the effect of reducing noise and recovering to a better degree the true covariance. And then one can also look at the time and space components, and this is where it gets interesting in terms of being able to analyze and build interpretive models for space-time processes. So here we just show the principal KPCA factors for both the A Kronecker B covariance and then the inverse, which is the inverse of A and the inverse of Kronecker inverse of B. The inverse, as we know for the MIE, has to have sparse behavior. And so here's the temporal behavior over 12. It's 12 by 12 covariance. We have this scaling, which is just tridiagonal, right? Everything else is covariance is inverse covariance is 0 entries, and we have this pentadiagonal structure on the inverse of the spatial component, the B. And when these are the estimates using 1,000 realizations, again, for a sample covariance, and you can see there's pretty good agreement. All right, so I'm going to apply it now to this solar data, just for fun. And I'm not going to give you all the details, but we have 2 classes. We're going to look at a set of images, 16 by 16 images, and 10 time samples. And so what we see is that if we use a rank 1 Kronecker decomposition of Kronecker PCA, the top Kronecker factors for the MX class, these are the strong ones. And so these are all the whole video right before the flare where we don't include the flare. So we're looking at sort of precursors, susceptibility to big flares, right? That could be useful in guiding us to deciding whether there's any hope in being able to build a predictor. And then the B class are the weak flares. And you can see there's some differences you might see in the first Kronecker factors. in the inverse of the Kronecker factors, the inverse covariance, the precision matrix, we see this characteristic looks pretty tridiagonal here, maybe a little bit less up here with some heterogeneities in the variances over time. And then we have this, what looks like maybe pentadiagonal structure on space. So this looks promising. If we normalize these so that we look at the so-called partial correlation, where we normalize the diagonals, right, of all the variances are normalized to 1, and all of the elements of the inverse covariance are normalized to 1, then the situation looks a lot clearer. So we see that maybe this MIE model is not so bad. On the other hand, it doesn't look like there are any real obvious differences between the strong flares and the weak flares in their precursor time periods of 15 hours, of 9 hours. There's 1 hour cadence here. All right, so the next thing we should ask, though, is if we want a sparse model, is it really the right thing to be looking at the covariance, approximating covariance? Shouldn't we be approximating the object that we know must be sparse under this natural generative model with obeying a PDE? And so, of course, that is the inverse covariance that's sparse, which we call omega. So one could now talk about a different optimization. And here I'm going to assume directly that we have normally distributed, Gaussian distributed observations, hence the matrix normal in the title of the talk, because that gives us an objective function which is tractable. Frobenius norm of the inverse is not tractable, but the so-called penalized maximum likelihood objective function, which is this here, it will turn out to be, well, more or less tractable, as I'll discuss. So Sn again is the sample covariance built from our realizations, from all of our images, our videos of different MX class flares and different B class flares. We congeal them all into a covariance matrix over space and time and modality if we have modality. And omega is the inverse covariance, and we want to find the best estimate with a penalty, which that penalty is going to incorporate sparsity and structure. So there's a lot of background here that I'm not going to dwell on, but sparse estimation of inverse covariances has a very rich history, and it is the sparse covariance estimation goes back at least 15 years. The G lasso is one solution where this P just becomes an L1 norm on the matrix, right? So one can then look at sparse Kronecker products by incorporating a Kronecker product model into omega. One can look at Kronecker sums, which I'm going to talk about in a minute, and other types of approximations to omega, all with a sparsity penalty and a penalty parameter lambda to gauge how sparse we're satisfied, how sparse we have to be satisfied. So in a nutshell, the sparsity models are for the so-called Kronecker graphical lasso, graphical because the inverse covariance matrix, if it's sparse, can be looked at as a weighted adjacency matrix of a graph, where the zeros in that matrix correspond to pairs where there are no edges between them, right? And the non-zeros have edges with the corresponding weight of the inverse covariance. So the Kronecker G-lasso just uses the Kronecker representation, Kronecker product representation, with a sparsity penalty P on the off diagonals of A and B. The Terra lasso, that so-called tensor lasso, uses a Kronecker sum representation, which, as I'll describe in a minute, has the advantage, the big advantage, that it makes this objective function convex if you use an L1 penalty. Whereas with the Kronecker product G-lasso, the standard Kronecker G-lasso, it's not convex, right? You have a bilinear type of dependency of omega on A and B. And then sig-lasso, we're going to have omega be a square of a Kronecker sum, which I'll explain why in a minute. So the Kronecker sum, why the Kronecker sum? Kronecker sums are, as I say, linear in the Kronecker factors, A and B. I is the identity here, which is, of course, compatible. So this sum is compatible. A Kronecker I and I Kronecker B have the same dimensions. And it's generally, for fixed A and B, sparser than a Kronecker product model for that same A and B assumed to be sparse. So if you consider a very simple case, 3 Kronecker factors, A, B, and C, and we'll use these to approximate omega, the inverse covariance, using either a Kronecker sum or a Kronecker product, then you can visualize this, this kind of multiplication or explosion, as my student likes to call it, of edges that the Kronecker product representation causes. Because if you have an edge in A, so here's A right here, and as I said, zeros, which don't have asterisks in this matrix A, correspond to pairs where there's no edge. There's no edge between the first and the second node here, numbered from 1 to 4, and that's why you don't see a number here. That number is 0, right? So these edges are multiplied by the edges of B, which are multiplied by the edges of C. So you get this explosion of edges, this propagation. Whereas in the Kronecker sum, you only get a summation of edges, and therefore there's better control over the sparsity for a given sparsity of the Kronecker factors. That's sort of the intuitive explanation. So how do we approach this this problem from the point of view of an optimization? Well, we can state the optimization problem as OP2, which we call the Terra lasso optimization for tensor graphical lasso. We have the same objective function, omega, but omega is now restricted to lie in this cone, this positive cone, which is a cone defined by all positive definite matrices that have Kronecker sum representations of some kind for fixed dimensions, right? dk by dk. And then we have an off-diagonal penalty on all of the Kronecker sum factors with a rho k penalization coefficient. So one interesting interpretation of this optimization is that this corresponds to a maximum entropy model. This Terra lasso corresponds to the model where if you're only given modal projections of the data on each mode, so you have the matrices or vectors of each mode, you don't know how they combine into the tensor, then this model gives you a solution, which is the maximum entropy solution of the covariance, the inverse covariance under these assumptions of positive definiteness. So the Kronecker sum is a maximum entry type of model, if that makes you feel warm and fuzzy. We can solve this using some standard descent methods. Because it's a Kronecker sum, we have a convex objective function. For the rho k's strictly greater than 0, even if the sample covariance Sn is not full rank. And so we can use, iterative soft thresholding, which we do here, composite gradient descent with some standard settings. And we get a solution. We can also look at statistical convergence. So if we assume that we've converged to the solution, lambda omega hat is a minimizer of OP2, then if we impose that the regularization, the sparsity regularization at each mode of the tensor is of this form, that increases slowly in the dimension d, the total dimension, and decreases in the codimension, mk, increases logarithmically in the total dimension and inverse linearly in the codimension, and this is defined then as the square root. Then we have this sort of guarantee overwhelming probability, which can be specified by the dimension, a constant c, and the number of modes in your multi-way representation, time, spatial components, modalities, and so forth. The reconstruction error, and this is Frobenius norm here, omega 0 is the truth, is bounded above by a function that decreases in the number of samples, as it should, right? Get better as you have more samples, but it increases as the dimension, as log the dimension, or square root of the log dimension, as the square root of k. S is a sparsity parameter for the true model, omega 0, and the true inverse, that is, of the covariance sigma 0. So if you compare to G Lasso, there's one difference. This is almost exactly the same bound from the Frobenius norm as shown by Rothman and Levina, except for this term here, which is the minimum codimension. So if the dimensions are all sort of compatible, there's no real small dimensions, this codimension can be very large, right? So we get a very large improvement on the statistical convergence rate, the guarantee that this optimizer, this minimizer of this computational penalized maximum likelihood estimate actually is going to be close to the true sparse inverse covariance. And so you can just see here with an example, this is just a kind of a to show how scalable this Terra lasso method is relative to the big lasso is another competing method using Kronecker sum. The runtime in 124 seconds, we can run for sufficient sparsity a problem with over 1 billion variables, right? So 65 by 65 dimensions within each component. So we have a big speed up. The speed up can be mathematically characterized in terms of a product of dimensions is the standard G Lasso cost per iteration, whereas we have a sum of dimensions cost for the Terra lasso because of this Kronecker sum approximation. So the Sylvester G Lasso takes this one step further by saying that if you want a generative model, if you want a model that's interpretable, where you can say that the A and the B that you extracted correspond to some kind of, say, differential operator, incremental operator in a PDE equation that governs the realizations that the omega is the inverse covariance of, well, then we can note that the Kronecker product is a generative and interpretable model because we can interpret A and B, or at least the Kronecker, at least the Koleski factors of A and B, as ways to generate the process, right? By applying them to white noise, we can generate omega. We can generate realizations, I should say, that have inverse covariance omega. However, the Kronecker sum, despite the fact that it's so fast, is not generative or especially interpretable. The Sig lasso makes this into a generative model by assuming that the omega is the square of a Kronecker product. So this, for the two-way case, can be explained as follows. The inverse covariance omega of a vector z, where z has a Kronecker sum form, which is equivalent to this Sylvester equation. So Kronecker sums and Sylvester equations are intimately related, as you'll see in a minute. Omega is then the square, the inverse covariance is then proportional to W of assume sigma squared is equal to 1 here, is proportional to the square of this Kronecker sum. And Z is the output of a filter that is of Sylvester form, right? Left multiplication by filter coefficients A and right multiplication by filter coefficients B. If Z, for example, is a time by space matrix or flattened tensor. So this sig lasso exploits this Cartesian structure of differential operator, which can be seen by just looking at the Laplacian. So the Laplacian is simply the Kronecker sum of the second derivative with respect to x and respect to y of a planar process u. And that's equivalent when you discretize to a matrix, which is a sparse matrix of incremental operators, dx and dy double, x and y, which is equivalent through standard tensor algebra to this Sylvester relation. So this Sylvester relation says that this is equal to that, right? So then you can make that equal to W of white noise. Okay, so we have an optimization. We can go to the more general case by looking at the K-mode product generalization of the Sylvester equation, which is identical to the Kronecker sum of these factors, C1 and Ck, same as in the Terra lasso. Times the vectorization of this rectangular matrix Z is equal to some driving noise. And so we can write the objective function in the following way, with a slight change, and that is this is a so-called pseudo likelihood where we have removed the off-diagonal components in the determinant part of this objective function in the matrix normal model. So all we have is the product, or the sum, Kronecker sum of the diagonals, and omega then is the minimum of this function. We use cyclic coordinate descent, or you can also use proximal algorithms like alternating linear minimization. Palm. I'm not going to describe how the Sylvester representation allows you to solve this in a node regression fashion, just like the Munchausen-Bullman G-lasso. But one can do it that way if one wishes to avoid proximal descent methods. But we also get convergence and error rates. I'm running out of time, so I'm not going to dwell on this. But we get estimation consistency and sign consistency, all this shown in this paper appeared last year. That allows us to set the penalty terms proportionally to log of the dimension and inversely proportionally to n in this precise manner. Of course, we don't know the constants, but this at least allows us to sweep over different values of sample size and dimension, codimension size. This just shows that the sig lasso representation, the square of the Kronecker sum of two factors A and B that corresponds to sig lasso, is kind of achieving a compromise of sparsity between a Kronecker product, A Kronecker B, because 2 A Kronecker B is one of the components in the expansion of this quadratic, and a Kronecker sum. So we get this sort of this compromise between a Kronecker product and sparse Kronecker product and a Kronecker sum. This just shows that the if you're mismatched, you actually have a Kronecker sum and not a square of Kronecker sum representation for your inverse covariance, or a Kronecker product for your inverse covariance. That when you search over the regularization parameters for two different values of n, that the sig lasso achieves almost as good performance, and this performance is in terms of false positives and false negatives of detecting non-zero entries of the inverse covariance, as the true matched model, right? So these red curves are for sig lasso, and the peak of each one of these curves corresponds to its accuracy, right? That's where the corresponding regularization term would be, sparsity regularization term would be selected. So we don't do too badly in terms of the difference of the peaks for the red one, and the others is not too far away for the mismatched case. So the application I'm just going to finish with very quickly is for a case where we have videos of these active regions, these sunspots, 13 hours before a B class or an MX class of flare occurs, respectively. We have a lot of data here, over 20,000 dimensions, where we have time dimensions with 1 hour cadence. We have image dimensions, 100 by 50 images, sequence, 13 of them, 12 of them are pre-flare. And then we have 7 modalities, different channels, different wavelengths, different types of sensors on the satellite. And so we want to accurately estimate this inverse covariance using a Kronecker sum, which in the case of a multi-channel magnetic induction equation would look something like this. And we do, of course, model validation, data splitting, and cross-validation to report any results I'm going to talk about here. This just shows what we're doing. We have the 13th frame for the HMI channel, for the AI channel, for, let's say, a B-class flare. These are the frames we're going to use to build a predictor, and we're going to try to predict this last frame, right? And so this just shows the performance of the predictor. And how do we construct the predictor? We use the SIG lasso to estimate the inverse covariance. We then use that inverse covariance to construct the predictor using ordinary least squares. It's as simple as that. So ordinary least squares, you simply need the inverse of the covariate, inverse covariance matrix of the covariates, and the cross covariance, the cross correlation between the covariates and the predictee, right, which we have from, again, the inverse covariance estimates that SIG lasso gives. And so for this, I'm showing normalized root mean squared error for the SIG lasso with the palm, this proximal algorithm. And so, and the other algorithms, this is independent lasso applied to each pixel independently. So there's no spatial information at all. And as one would expect, you do terribly if you don't take account of any spatial correlation. And MX and B have quite different error behaviors in terms of their root mean squared error, but SGPOM does somewhat better in terms of normalized root mean squared error relative to the competing algorithms. These are just some examples that show the truth. And here's what we predict with SGPOM. 1 hour, we haven't seen it. We haven't seen the next frame. This is a holdout set, so we haven't used any of the pre-frames in the training. So this, looks pretty reasonable. This just introduces sort of for the solar physicists, we're very interested in how valuable the HMI channels are, because this data is expensive. If you threw in the HMI channel or you threw it out, would you gain or lose respectively in terms of performance? And what we show is you gain by about a factor of 20 for B-class flares and about a factor of 9 for MX class flares in terms of prediction. And then finally, how does this relate to classification? Well, we can use the inverse covariance estimates as our inverse covariance in the QDA, right? Quadratic discriminant analysis, which is just a hypothesis test, a most powerful hypothesis test for the case of simple hypotheses implemented through a likelihood ratio. And when you do that with the SIG lasso estimates, you get substantially less error in terms of classification of unseen precursors to flares of either MX or X type, X or B type. So that's all I have to say today. My conclusions, I'm not going to belabor them because I've harped on them all the way through. I'll only say that these multi-way covariance models, especially the motivation of the inverse covariance as the sort of the appropriate quantity, if you're interested in sparse approximation, is justified by the mathematical physics that underlies the process that you're trying to analyze in terms of second order covariance matrix normal approximation. So I'll leave it at that and entertain any questions anyone might have, or discussion, comments, criticisms. I know Carrie's in the wings there.
Heckle.
Heckle.
No, that was very nice. Thanks, Al.
You're welcome.
We thank you, Professor Dr. Harrell.